In this video, we're going to take a look at some additional examples computing the values for sine and cosine of angles using the sum and difference identities. In this first example, we are being asked to find the exact value of the cosine of 195 degrees. If we think about the 195 degree angle, we should be able to see pretty quickly that this is not an angle that we're going to readily know the cosine value of. This angle is a little bit more than 180 degrees, so it's going to be a third quadrant angle. And it's easily seen that the reference angle here is going to be 15 degrees. And so in order to use reference angles to find this, we would need to know the cosine of 15 degrees, which we do not. And so the easiest way to do this then would be to write 195 as the sum or difference of two angles whose sine and cosine values we know, and then use the sum or difference identity, whichever is appropriate. In this case, there's a number of ways we can do this. One way is to observe that this is equal to 45 degrees plus 150 degrees. Right? And if we make this decomposition, we know that the cosine of 195 degrees will be the cosine of 45 degrees plus 150 degrees. Right? And so this will be cosine of 45 multiplied by the cosine of 150 minus the sine of 45 times the sine of 150 degrees. And now we just need to know all of these values, which we can easily figure out. The cosine of 45, of course, is square root of 2 over 2. The cosine of 150 degrees, we might have to think about for a moment. This is an angle in quadrant 2, and in quadrant 2, cosine is negative, so I know cosine of 150 degrees will be a negative value. And the reference angle for 150 degrees is 30 degrees, and the cosine of 30 degrees is the square root of 3 over 2. So combining the fact that cosine is negative in quadrant 2, along with the fact that cosine of the reference angle, 30 degrees, is square root of 3 over 2, we see the cosine of 150 degrees is negative square root of 3 over 2. The sine of 45 is square root of 2 over 2. And the sine of 150 degrees is going to be the sine of 30 degrees, the reference angle, which is 1/2. And it's going to be positive because in quadrant 2, sine is positive. And so we have this expression here, which we can simplify as the negative square root of 6 over 4 minus the square root of 2 over 4. And then, of course, adding or then combining these terms together, and we get negative square root 6, minus square root 2 all over 4. And this is our value for the cosine of 195 degrees. Notice that this will be a negative number. That numerator, we have negative 6 minus negative square root 6 minus square root 2, and that will be a negative numerator divided by 4 will result in a negative number. And this makes sense because this angle, 195 degrees, is in quadrant 3, and cosine should be negative there. So we get a cosine of 195 degrees to be this negative number, negative square root 6 minus square root 2 all over 4. In this example, we're asked to find the exact value of the sine of pi over 12 radians. This is the first example we've looked at, which involves an angle involving radians. And by their nature, it's a little bit more difficult to write an angle as the sum or difference of two other angles in radians than it is in degrees. But here's a strategy that will always work in order to help make this process as simple as possible. We know that we have the common angles of pi over 6, pi over 4, pi over 3, and pi over 2. And typically, we will want to write our angle as a sum or difference of two of these four angles. What we can always do is rewrite each of these to have the same denominator as our given angle. So in this case, we want to write each of these as a fraction of pi over 12. And so we can do that here. We have pi over 6 is going to be 2 pi over 12. Pi over 4 is going to be 3 pi over 12. pi over 3 will be 4 pi over 12, and pi over 2 will be 6 pi over 12. And now this is a lot easier to see how to write pi over 12 as a sum or difference of two of these angles. We could write pi over 12 as 3 pi over 12 minus 2 pi over 12, which would be pi over 4 minus pi over 6. Or we could actually write it as 4 pi over 12 minus 3 pi over 12, which would be pi over 3 minus pi over 4. So either of these decompositions would work and would write pi over 12 as a difference of two angles whose sines and cosines we know. So let's use our first one, and let's write pi over 12 as pi over 4 minus pi over 6. So the sine of pi over 12 will be the same as the sine of pi over 4 minus pi over 6, and we can apply the difference formula for sine on this expression. So we would have the sine of pi over 4 times the cosine of pi over 6 minus the sine of pi over 6 times the cosine of pi over 4. And these are all values that we should readily know. Sine of pi over 4 is square root of 2 over 2. The cosine of pi over 6 is the square root of 3 over 2. The sine of pi over 6 is 1/2. And the cosine of pi over 4 is the square root of 2 over 2. And simplifying this expression, we end up with the square root of 6 minus the square root of 2 all over the common denominator of 4. And so the sine of pi over 12 is the square root of 6 minus the square root of 2 over 4. Now we used that pi over 12 was pi over 4 minus pi over 6 here. As we previously saw, we could also have used that it was pi over 3 minus pi over 4. And if we use that decomposition and use the difference formula for sine with those different angles and simplify, we'll see that we do indeed get the same exact number. Feel free to try that on your own if you'd like. This example is a little bit different than the previous ones. Here we want to find the exact value of the expression cosine 70 degrees multiplied by cosine of 50 degrees minus the sine of 70 degrees times the sine of 50 degrees. Clearly, we don't want to use the sum or difference formulas in the same way as in the previous examples, but rather we want to use it sort of in the reverse direction. What we notice here is we have two different angles in this problem, a 70-degree angle, which I'll call A, and a 50-degree angle, which we can call B. And this expression has the form cosine A, cosine B, minus sine A, sine B. This expression should look familiar as it's part of the identity for the sum identity for the cosine. And so this is equal to the cosine of A plus B. Recalling that A and B are 70 degrees and 50 degrees respectively, this is the cosine of 70 degrees plus 50 degrees, which is 120 degrees. The cosine of 120 degrees is a second quadrant angle. So in second quadrant, cosine is negative. So we know that this will be a negative value. And the reference angle is 60 degrees, meaning it has, other than the negative sign, the same cosine as 60 degrees. So it must be equal to negative 1/2. So this example does indeed use the sum formula for cosine, but it uses it in the reverse direction to replace an expression of the form here with a cosine of a single angle whose cosine we can evaluate. If you'd like some additional practice of the examples in this video, you can try the following in finding the exact values of sine of 15 degrees, the cosine of 7 pi over 12 radians, and the sine of 37 degrees times the cosine of 53 degrees, plus the sine of 53 degrees times the cosine of 37 degrees. The answers will appear in just a few seconds. So sine of 15 degrees, we could rewrite 15 degrees as either 60 degrees minus 45 degrees or 45 degrees minus 30 degrees. And in either decomposition with the sine, the difference formula for sine, we'll get a result of square root 6 minus square root 2 all over 4. 7 pi over 12 is equal to pi over 4 plus pi over 3. And applying the sum formula for cosine, we see that that is equal to square root 2 minus square root 6 all over 4. And the expression at the bottom has the form of the sum formula for sine. So that would be equal to the sine of 53 degrees plus 37 degrees, which is the sine of 90 degrees, which is 1.